All right, so where did we get? We got as far as drawing fructose. Um, the next step, again, the enzyme name and the reagents sort of tell you what's going to happen. Phosphofructokinase tells you that we're going to add a phosphate to fructose 6-phosphate, which is phosphofructose. That's another way. It would have been lovely if they had called this fructose 6-phosphate kinase, but there are no nomenclature rules for enzyme names, so we're stuck with what whoever discovered it decided to call it and what the people that argued about it afterwards changed it to. So we know that ATP's got to be transferred. You can figure that out. Now, what would be confusing is if you didn't remember, and this is a memorized detail, which of the oxygens gets the phosphate. Here's a clue. Remember that in the next step, aldolase, we're going to convert the 6-carbon molecule into 2 equal 3-carbon pieces. So it's going to make the most sense to have phosphate groups on carbons 1 and 6 for symmetry's sake, so that we can split the molecule in the middle and then both ends of it have phosphates on them. So this one is fructose 1,6 bisphosphate. And the next phosphate group goes on the, sorry, say that again? Bis means 2 phosphates, yep. Fructose 1,6 bisphosphate. And people have asked, do I need to draw the open chain form and or the closed chain form? Either is okay. I think open or closed chain is probably easier, but either is okay. If you draw the mechanism of this aldolase reaction, you have to go to the open chain form first, because the aldolase reaction happens on the open chain ketone form. All right, so what are my 2 products? I drew one of them, glyceraldehyde 3-phosphate.
Dr.
Yes?
If on that fourth box, if you were to draw it in open chain form, would that be wrong?
No, it would not be wrong to draw it in open chain form at all. Open chain form's in equilibrium with closed chain form, so that's fine. And because I know you like things guaranteed, open chain form OK2. The drips of blood are getting bigger. All right. Grizzly. Okay, so, yes. Yep. Did it. Okay. So, by the way, which carbons in fructose 1,6 bisphosphate become glyceraldehyde 3-phosphate? Do you remember? Did you say it? What did you say? 4. Did you not say anything? Okay, yeah, it's 4, 5, and 6 actually. The way you can tell that is to remember, let's just look at, I'll draw the open chain form for you of fructose 1,6 bisphosphate. Five, 6, 4, 3, 2, 1. Okay, and remember the pattern you're looking for in a retroaldol reaction. The bond that you're going to break is the bond between the alpha and the beta carbons. So this is the bond that's going to get broken. And the beta carbon, after the reaction, is going to become a carbonyl carbon. And the way that happens is a base removes the proton, electrons kick down, and then enolate leaving group leaves. And if you want, you can show that enolate leaving group getting protonated as it's leaving. This carbon, carbon 4, becomes the carbonyl carbon. This oxygen, carbon 1, becomes the carbonyl oxygen, on the oxygen on carbon 4. And then look at the two things attached other than the oxygen and the bond that gets broken to carbon 4. It's a carbon and a hydrogen. So carbonyl carbon 4 becomes an aldehyde. So the carbons 4, 5, and 6 of fructose 1,6-bisphosphate become glyceraldehyde 3-phosphate. That's the left-hand side of the molecule. And then the other side is just carbons 1, 2, and 3, and that's dihydroxyacetone phosphate. Okay. And somebody asked what happens to that, and the answer is it gets converted to glyceraldehyde 3-phosphate, and the mechanism for that is, as you recall, tautomerization through an ene-diol intermediate that we talked about. 2 tautomerization steps. Okay, so everything from this point on happens twice in the cycle because we end up with 2 molecules of glyceraldehyde 3-phosphate. What's the product of this step? This one's hard because you don't have any enzyme name hints. The enzyme name here says glyceraldehyde 3-phosphate dehydrogenase. I forgot to call this dihydroxyacetone phosphate. This one's hard because you don't have, you know from the enzyme name that it's going to oxidize glyceraldehyde 3-phosphate. And another hint is the starting material has phosphorus in it. And then the last hint is that the next product is going to deliver a phosphate to ATP. So this one you may have to memorize. This is like glyceraldehyde 3-phosphate. The only difference is that the carbonyl carbon, instead of being an aldehyde, gets oxidized to an acyl phosphate. That's 1,3-bisphosphoglycerate. So you may have to memorize that. If you've got that, then you notice that this enzyme is called, the next enzyme is called phosphoglycerate kinase, but I told you it's named for the backward step. You can see that this in the forward direction, ADP is going to be the nucleophile, and it's going to attack this phosphoryl group, and everything over here is going to be a leaving group. That phosphoryl group becomes the gamma phosphate of ATP. All of this is the leaving group. So there's ATP, and then what's left is just this molecule, which is called 3-phosphoglycerate. So phosphoglycerate kinase can run in this backwards reaction. That would involve transfer of a phosphate group, the gamma phosphate group from ATP, to the carboxylate oxygen to make this acyl phosphate. Yeah?
Do we leave the oxygen with a negative charge and not protonate it because we're just going to deprotonate it the next step?
Right. Do you leave the oxygen with a negative charge? Yes, because the pKa of the carboxylic acid is 4 and we're at physiological pH. Yes?
For the last step, could you kind of look at it as like a reverse hydrolysis? I guess it says
Yeah.
it's a dehydration, but is it kind of like
right, the term hydrolysis you're using, where's that coming from?
Just because there's H2O.
Sorry, which step are you talking about?
Oh, the one with the glyceraldehyde phosphate and the dihydroxy.
Oh, the interchange here between these two?
Doing the opposite and connecting them?
All right, as I've said, you're cutting and I'm not bleeding, so so try again and I'll see if I can get it. I'm just dense, so sorry.
Never mind. I think
No, go for it.
figured out my own voice.
Go for it, try again.
Well, I'm just thinking like if you split them apart, I guess it depends on what you use too.
Splitting them apart here in the previous step,
Yeah, like it's
in the aldolase reaction.
yeah. Is it kind of like hydrolysis?
In a way, it is because you're breaking apart two things, and we've done hydrolysis of like esters before, breaking apart two things. So it's similar in that respect. The only reason I wouldn't call it hydrolysis is just that water. In a hydrolysis reaction, you add water to something and kick something else off. And in this case, we're just using a base to remove this proton, electrons kick down, this bond breaks, and we pick up a proton. So there's no addition of water step. But there's a connection you're seeing that I'm missing. So if you think about it, raise your hand again, because I want to make sure I understand. Okay, yes.
I'm just wondering, is once the dihydroxy acetone phosphate, do we just not worry about that for the rest of the?
Well, the reason we don't worry about it is because all of this gets converted to this.
Yeah.
Yep. And we went through that mechanism. It turns out tautomerization via an ene-diol intermediate is also the mechanism by which you interchange glucose and fructose. So that's two steps that have a similar mechanism. All right. Did I miss others? Yeah, go ahead.
If we don't have to worry about it for the rest of the chain because it just comes back into the glyceraldehyde and phosphate, what's the point of knowing that dihydroxy phosphate has?
You're right. Since it turns into this anyway, what's the point of knowing it? And the point is there is an enzyme, and it's actually one of the most efficient, perfect enzymes in the world. People measure enzyme efficiency, and once the enzyme is as fast as it takes for things to diffuse through water, it's called a perfect enzyme. And triose phosphate isomerase is one of those. So its job is to catalyze the interconversion. Otherwise, dihydroxyacetone phosphate would accumulate. And I think the other thing, I don't remember if we learned this semester yet, you'll see when we do lipid metabolism that the glycerol portion, I think from metabolism, first becomes dihydroxyacetone phosphate. So anyway, it's a real intermediate, but you're right, for the progress of glycolysis, everything, it all gets converted into glyceraldehyde. Yep. All right, others that I missed? Okay, so 3-phosphoglycerate, phosphoglycerate mutase. What does that one do? That one's maybe easier to remember. You pop the phosphoester off the C3 hydroxyl, and you put it onto the C2 hydroxyl. So that's going to become 2-phosphoglycerate. I'm just going to abbreviate the phosphate group like that. All right. And then enolase. Do you remember what that does?
Yes.
Ish. That's a dehydration reaction. So that's going to remove this hydrogen. Oops. And this OH group. We drew the mechanism for that one in the previous lecture on the quiz. A base deprotonates this alpha proton, you get an enolate, and then the enolate electrons kick down and OH minus leaves and picks up a proton while it's leaving. And so the next molecule is this one. And a clue to its name is in the name of the enzyme. This is phosphoenol pyruvate. And the thing to remember about this one is this is an unusually unstable or an unusually reactive phosphoester. We talked about protonating on the alpha carbon to turn the oxygen into a really, really great leaving group. And then ADP comes in and acts as a nucleophile, attacking this phosphorus, this phosphoryl group, which becomes the gamma phosphate of ATP. And then electrons kick down to liberate the leaving group, which is pyruvate. Okay? And then, after the pyruvate dehydrogenase complex, what do I have in this box? Yep, that's acetyl-CoA. One of my carbons from pyruvate is lost as CO2, and the other two carbons remain behind as the acetyl group in acetyl-CoA. All right. Yes?
It's just, I feel like it's easier to say it with the mechanism. Can you just go between, I guess, box 8 on the right side and box 9 for the middle lanes?
Okay, you want to go between phosphoglycerate and phosphoenol pyruvate?
Yes.
Yeah? Okay. Sure. So we might, if you wanted to, you could show this mechanism as follows. A base removes the proton from the carbon that is alpha to the carbonyl. You could draw the enolate as an intermediate if you wanted to. It would lack this proton and have a negative charge on this carbon. Alternatively, and that enolate's an intermediate, so maybe I will draw it, and then I'll show you maybe an acceptable alternative. When I give you acceptable alternatives, you got to trust me that I'm not going to put two acceptable alternatives as options and make you choose between them and guess what I'm thinking, because that's not fair. So here's that enolate intermediate. Then electrons on the negatively charged alpha carbon kick down and OH minus leaves. And while it's leaving, it picks up a proton from some acid, perhaps the conjugate acid of the base that did the deprotonating. Yep.
And it makes the H2O.
And that makes H2O. Yep.
Yeah.
All right, good. Okay, so that was kind of hard. That's a wake-up call about what you need to be practicing on. And again, the goal here is not for me to determine whether you can copy things down, because of course you can. Everybody can do that. But the goal is to see, can you understand, can you predict, do you remember what's happening, how it's happening, which is mechanism, and then why it's happening. So if we were to go back and look at this list, I might ask you, step 1, this is now what is happening. Tell me about what you expect for the energy of this step. And in particular, you should focus on what's changing. For example, in step 1, you notice that I've got in ATP a phosphoanhydride involving the gamma phosphate group of ATP, and that gamma phosphate is now here in the product glucose 6-phosphate, and it is now a phosphoester. So level 1 changing to level 2, you predict that to be downhill, right? In contrast, for the next step, glucose to fructose, an aldehyde to a ketone, essentially. Those are both level 1, so probably no change, probably neutral, right? How about step 3, fructose 6-phosphate to fructose 1,6-bisphosphate? You predict what? Uphill, downhill, neutral? Downhill, okay? And I've been asked, how do I know what to focus on here? You don't focus on the C6-phosphate because it's not changing. Again, you look at what's changing. I have in ATP a phosphoanhydride involving the gamma phosphate group. And then in the product, that gamma phosphate from ATP is involved in a phosphoester. Again, that's level 1 to level 2, so that's downhill. Yeah?
Wouldn't technically like the fructose 6-phosphate going to fructose 1,6-biphosphate or bisphosphate be uphill, and that's why you need ATP to cover it?
Sure, from the perspective of if nothing else were there, going from the alcohol to the phosphoester, you're paying for that by using ATP. So all of this level 1, level 2 comparison is sort of one-sided. We're focusing on the electrophile in the starting material and then what the corresponding electrophile is in the product. Ideally, if we were going to do this for real and calculate numbers, we'd look at the stability of all of the products versus the stability of all of the starting materials. Yeah?
Looking at the arrows, can we just assume that any arrow that is just pointing to the right is downhill, and then any that has both arrows pointing?
Yeah, the way I've drawn it, and I may conceal that on an exam because I may want to ask you which steps are downhill, but as written here, the arrows that are reversible, well, no, there's an exception. I didn't do that very well here. This step is also reversible. The only steps that are not reversible are the ones with the asterisks, because whatever, the little stars. First, third, and last. And then, yeah, the pyruvate kinase step is irreversible because you lose CO2. The aldolase step is reversible. You're going from basically a ketone to a ketone and an aldehyde. The oxidation step to the acyl phosphate is reversible because you're going from a level 1 aldehyde to a level 1 acyl phosphate. This step is reversible because you're going from a level 1 acyl phosphate in 1,3-bisphosphoglycerate to a phosphoanhydride. Again, focusing in on what's changing. Before the reaction, you have a phosphoryl group here in 1,3-bisphosphoglycerate. After the reaction, that is now the gamma phosphate group of ATP. What used to be involved in an acyl phosphate, it's now involved in a phosphoanhydride. Level 1 to level 1, that's reversible. Okay, go ahead. Do you need to memorize the full-length structure of ATP? You should be able to recognize it. I'm not going to push you on the structure of the base adenine part of ATP yet. We'll do that later in nucleic acids.
Like, will it be, I guess, available, or will it be just know?
Good question. What I probably will do is have in a box structures of various cofactors and their names, and then you can use them as needed. All right. Great. This reaction, 3-phosphoglycerate to 2-phosphoglycerate, is reversible because you're going from one phosphoester to another. The dehydration reaction is reversible. There's not a strong free energy change there. There's less really to compare to there in terms of making that assessment. And then finally, the pyruvate kinase step goes from an unusually reactive phosphoester to a ketone and a phosphoanhydride. Again, this phosphoryl group that's involved in this unusually reactive phosphoester ends up as the gamma phosphate of ATP. And so you're going from a phosphoester to a phosphoanhydride. We talked last time about why that reaction is so downhill in energy. It has to do with two things. First, the repulsion of charge between the carboxylate and the phosphate group. And then second, it has to do with the fact that when you protonate this phosphoester on the alpha carbon, this becomes an excellent leaving group and is very, very reactive. Much more like an acyl phosphate than a phosphoester. So this reaction ends up being sort of level 0. Because phosphoenol pyruvate is unusually reactive, we'll call it level 0 to the level 1 phosphoanhydride in ATP. Okay, so I don't know. This isn't meant to be discouraging or downhill, a downer, but experiences like this can teach you where specifically you have work to do to prepare for an exam. The question all of you want to know is what's going to be on the exam and how can I get the points? And I have just disclosed to you a major portion of what's going to be on the exam and how you can get the points. There'll be fill in the box questions, all right? So, yes?
Are the fill in the box questions going to come along with like the specific names for each molecule?
Let's see. So I could, though in a multiple choice format, it's a little bit hard to do that just because there's so many variations. What I generally might do is not give you the names, but give you perhaps enzyme names, arrows, some of the reagents like I've done here, and then have you fill in the structures without the names. Or in another format, I might not require you to put in the structure, but might require you to put in the name. And you'd be choosing from a list of names, some of which are real, some of which are the correct names but for the wrong molecule, and some of which don't even belong in glycolysis or are made up. And same thing with the structures. You'll have options A through whatever. You'll have to choose which structure goes where. Some of them will be correct, some of them will be close but wrong, others will be like that's a real molecule but it's not involved. Yeah.
So you want us to know the 12 molecules, structure, name, how it gets in between, not like the arrows in the
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
And then
For those 12, yeah, you need to know their structures and their names.
and you want us to know the 11 enzymes.
I want you to know the 11 enzyme names. I want you to know which steps are downhill and why. And then I want you to be able to answer mechanism questions. We've spent the past 2 times in class together going through the mechanisms. This is a review of the what. Mechanism, which you can review from your notes from the 2 previous times, is the how. And the level 1 versus level 2 and so on comparison is the why. Are we going downhill or not? Yeah.
Can you just quickly show the arrows from going from the phosphoenol to the 9th box to the 8th box to the 9th box?
Which I'm
Sorry, the 2.
1, 2.
next to
Give me a
amylase and pyruvate kinase.
this one.
Yeah, I'm just a little confused on how that works with ADP not to put in.
Okay, great. So yeah, and this is one we did last time, so you can look there too for a little bit more detailed explanation. I would draw it this way. You can condense it, but I would draw it this way. The following arrows show you how you can draw a resonance structure of phosphoenol pyruvate that looks like this. Those are just resonance arrows, okay? Showing you that this carbon that is alpha to, that this carbon that is alpha to the carbon that bears the oxygen in pyruvate is electron rich. So then those two are resonance structures of each other. I would then show, I would then show the alpha carbon getting protonated by the enzyme. That then turns all of this into a really good leaving group. How can you tell it's a good leaving group? Well, first notice that if it left like this, it would leave as a neutral molecule. What would its, this is the leaving group. To determine if it's a great leaving group, think about its conjugate acid. The conjugate acid would have a pKa, you don't have to memorize this, but the pKa of that would be -2 or -3. So that's an excellent, excellent leaving group. Most of the leaving groups we've dealt with so far have been in the range of like pKa of conjugate acid around 7 or 8. So this is, and you can just memorize this point without justifying it, that the neutral pyruvate is an excellent leaving group. That now activates the phosphoryl group to being attacked by ADP. So how are we going to draw ADP? This is fine. You can just draw the beta phosphoryl group that acts as the nucleophile. Lone pair electrons on one of the negatively charged oxygens attack the phosphorus, break the pi bond. We get an intermediate in which phosphorus is bonded to 4 to 5 things. And one of those 5 is ADP. Again, this is the beta phosphoryl group of ADP. This is going to become the gamma phosphoryl group of ADP. Negatively charged oxygen is going to act as the kicker offer. Electrons kick down. Excellent leaving group leaves. That gives us pyruvate and ATP. So embedded in that is some unfamiliar stuff. The stuff with pyruvate and how to turn the phosphoester into a good leaving group. That's new. The attack of a nucleophile on a phosphoryl group, an intermediate, and then kick down in an elimination step, that's not new. That's similar to stuff that you've seen. Okay. All right, so a little bit of work cut out for you. That's kind of fun. Let's spend the next little bit just seeing, again, no peeking. Obviously, all the answers for what's on the back of your quiz are contained on this page of the quiz, but again, I'm not interested in your ability to copy things down. See how well you can name these enzymes based on the substrates and what they do. Some of these you can memorize, some of these you can figure out on your own. This is going to be a good way for you to identify what you need to study. So sometimes you can solve these a little bit piecemeal by focusing first on what the enzyme is doing. Ignore the substrate part of the name and just focusing on what the enzyme is doing. For example, in the first step, that's transfer of a gamma phosphoryl group from ATP to an alcohol to become a phosphoester. What kind of enzyme does that? What's the name for that? That is a kinase. So at least at the beginning, if you don't remember which kinase it is, you can at least remember that it is a kinase. What are the other kinase steps in glycolysis? Yeah, look for all the ATPs. It's that easy, right? So fructose 6-phosphate to fructose 1,6-bisphosphate should also be a kinase. 1,3-bisphosphoglycerate to 3-phosphoglycerate. Now there you're converting ADP into ATP. You're going from an acyl phosphate to ATP, but in the backwards direction that would still be transfer of a gamma phosphate group from ATP to the carboxylate. So this is a kinase as well. And similarly, the final one is also named as a kinase, again for the backwards reaction, because if you start from pyruvate and go backwards, transferring the gamma phosphate group from ATP to this phosphoester, that's also kinase. So yeah, 4 kinases, and then all you got to do is remember what the right molecule is. Go ahead.
Wait a minute.
Another key is to look for the steps that involve NAD plus and NADH. Those are always, yeah, go ahead.
Can you remind me what aldolase does?
Yeah, aldolase catalyzes the reversible retroaldol reaction, where we split the beta hydroxycarbonyl in fructose, 1,6-bisphosphate, into dihydroxyacetone phosphate and glyceraldehyde. So aldolase goes there. Now, aldolase is pretty specific. The way you're going to have to remember that is to remember the reactive pattern you're looking for a starting material in the retroaldol reaction. That is a beta hydroxycarbonyl compound, and you're going to look for the breaking of the bond between alpha and beta carbons to give you the product. That's a key indicator of an aldol reaction. NADH involved reactions, NAD plus and NADH involved reactions, what are those usually called? Dehydrogenases. Yeah, anything that's a lot of redox reactions are that involve NAD plus and NADH, dehydrogenases. Okay, so that would be these two. And then what else have we got to fill in here? What's this one called? That's called an isomerase because there's no ATP or other cofactors needed. You just need the enzyme, and you're switching from aldehyde to a ketone. Similar change here, and actually similar mechanism. There's a couple others. This one that moves the phosphate group is a mutase. And then this one that does the dehydration to get phosphoenol pyruvate, enolase. Good. Now, it's up to you to go back and get the right substrate names as appropriate in those names. But you're seeing how a knowledge of what's happening can help you remember what the right enzyme name is. Okay. Good luck. Happy Memorial Day. I'll see you Tuesday. Don't do too much OChem over the weekend.